Thank you very much, and thank you to all the organisers. It's a great pleasure to be here tonight and on the same platform as Henrik. Now, in this talk, I'm actually going to start off talking a little bit about science, and in particular, science in the modern world, because I do think that a lot of the misconceptions about climate science are actually misconceptions about science in general. So bear with me to start with. So what is science? Okay. If you look at dictionary definitions of science from 100 years ago, they all concentrate on the fact it comes from Latin for knowledge, and it is knowledge, but it's a knowledge of a certain type that's arrived at in a certain way. And then over the last century, increasingly, the words science community and science consensus crept into the definitions, particularly led by this man who was a condensed matter physicist from New Zealand. So what is science consensus? I searched around for a dictionary definition, and I found this on Wikipedia of all places, and I think it's excellent, okay? The collective judgment, position, and opinion of a community of scientists in that particular field. That matters. Scientists often don't realise that their expertise and skills are very well honed to their discipline, and they think they can apply it somewhere else, and it's quite often not a good idea. So in that field of study is an important caveat. It implies general agreement, though not necessarily unanimity. Now, this is my community. It's actually one of two communities I belong to, because I'm a solar terrestrial physics, and this is the world's solar physicists that we got together for a meeting in Bournemouth a couple of years ago. And there are some things about the sun that everybody in this picture would agree on. Everybody. There's some things that 95% would agree on. We'd say there's a consensus, but not unanimity. And there are some things we don't agree on. And of course, if we had unanimity, we wouldn't need to meet to discuss, would we? There'd be nothing to discuss. And so there is always that element to science that there's an edge where there isn't consensus. Why it's important is a lot of people have an image of science that's based around, particularly this man, a sort of lone wolf who turns everything upside down. It was actually never thus, okay? Einstein, there were a whole load of people pushing at the doors he opened, okay? And as actually even Newton managed to say, he saw further than most by standing on the shoulders of giants. And that was true of Einstein. So that model is wrong, and the modern model for science is very much the consensus model, okay? There are reasons for that. If you look at Einstein's miracle year in 1905, the number of scientific publications was smaller than that in the year 2000 by a factor of about 1 million. Okay? Science has become much more discipline-oriented, it's become interdisciplinary, multidisciplinary, and there's just much more of it. And that's why one individual doesn't matter as much as the consensus. So how do we arrive at this famous consensus? And it's through a process that I think, and many others do, is Britain's greatest ever contribution to science, and that's peer review. Okay. It was actually introduced, ironically, by an immigrant to this country, Heinrich Oldenburg. He was the first secretary of the Royal Society and the first editor of the world's oldest scientific journal, Phil Trans. And he started pushing things out where there wasn't consensus to his friends and fellows of the Royal Society to see who thought what should be published. And his ideas were then taken up by Sir Roger Bacon and John Deere and formalised into what we understand today as peer review, what we would recognise today, first applied to medical observations by the Royal Society of Edinburgh. Why is it so important? Well, to put it in modern parlance, it's the way science expunges fake news. Okay? It's incredibly frustrating, peer review. It's often flawed, it's slow, it drives you mad as a scientist, but it will get rid of what's wrong in the literature record over time for a certainty. Sometimes it does it very quickly, like cold fusion. Sometimes it takes a long time. And if you want to know what would have happened without peer review, I'll give you the internet, okay? It's not an information highway anymore, it's a misinformation highway. There's more wrong on the internet than there is right, as observed by Randall Munro here. Okay, so that's why peer review is important, that's why consensus is important. Well, let me actually give you an example. Let's go back to Einstein again for a moment. Einstein's relativity, introduced in 1905, and then general relativity 10 years later, and it kind of divided the scientific opinions. There was people greatly for, people greatly against. And in 1919, Sir Arthur Eddington here discovered what we now call gravitational lensing, a prediction of Einstein's theory that wasn't in Newton's. And the consensus started to shift very, very rapidly behind Einstein. An element that people don't realize is Einstein was a liberal pacifist Jew, and I'm afraid in the 1920s that was not popular around the world, but especially in his native Germany. There were public outcry about it. Believe it or not, Einstein's relativity was described as Jewish physics. It was all a Jewish plot to befuddle us, to make it easier for other Jews to take our money, our women, and our jobs. Seriously, this actually happened. There were huge events. Einstein became so fearful for his life, he stopped talking in public. Okay? And there were one or two scientists behind this, particularly Leonard and Stark, who actually both joined the Nazi Party. They were Nobel laureates, though. Okay? But they wanted Aryan physics instead of Jewish physics. It's as if physics understands the concept of race. I mean, it sounds ludicrous today, but it happened. It really happened. And it spread around the world. Now, I'm not saying this man was anti-Semitic at all, but he was very arrogant and misguided. He was, like Eddington, a former president of the Royal Society, and he taught relativity, at least what he thought was relativity, at Imperial College, but he got it wrong. And it took a while for it to emerge that it was wrong, and eventually decided he didn't like relativity. And he found himself not being able to get published and outside the consensus, and he started talking about cozy clubs, and then cabals, and then conspiracies, and then mafias, and even scientific fascism at the end, okay? Nowadays, you never hear his name. He's disappeared from the literature. The only place you'll find him is on the internet, where people pop up saying, hey, Dingle was right. No, he wasn't. It makes me laugh. Those people probably have one of these, a sat-nav. And sat-navs make a correction for Einstein's relativity. And if you didn't, your position would get wrong by 2 kilometers every day, extra every day, because of special relativity, and 13 kilometers a day because of general relativity. Interestingly, the sat-nav system was first started to be designed the year Dingle published a book, which is a rant against relativity, but he was ignored. They went with the consensus view. They didn't go with the relativity deniers. And that's really important because we have sat-nav as a result. Well, at least we might have had a sat-nav before, but it was one that would have put you in the wrong country after a month or so. Okay? So consensus really matters. It matters for science progress, and it matters for getting science into technology that can help mankind. While I'm having a bit of a rant about the internet, I just want to talk about, has anybody come across MRDA? Okay? It stands for, it's kind of close to my heart, because my father used to work for John Profumo. And MRDA stands for Mandy Rice Davis Applies, okay? That's supposed to spin up like a newspaper in an old movie. I'm not sure it worked, okay? But it comes from the famous quote that she made at the trial of Stephen Ward, he would, wouldn't he? Which is what she actually said, okay? And it's used, for me, it's a whole way of marginalizing a scientist who's saying what you don't want to hear. Okay? He would say that, wouldn't he? Okay? And it's amazing how it spreads. I get emails telling me I'm only going on about carbon dioxide because I'm a Marxist and I want to bring down the capitalist system. I think, really? I'm sorry, if anybody starts talking Marxist doctrine, it bores the pants off me. And actually, that was quite nice because the letter then went on to threaten me and my family. And I thought, well, okay, if you think I'm a Marxist, you don't know who I really am, and so I'm not going to take it seriously. Or I'm told that I'm only doing it for the money, which is really interesting because I've never had a research grant, a penny of research money, to do any work on climate change. I've never asked for one. Okay? So I might say why I do it. Okay? Two things that Mandy Rice Davis and people who use MRDA don't know about scientists. Okay? One, what every scientist longs for, what we live for, what we want is to be famous for being right. What every scientist dreads is being notorious for being wrong. Okay? And the only way that you have a chance of avoiding two and actually maybe even get a shot at one is demands that you're brutally honest with yourself. And actually, if I'm not, I get a little voice in my ear, and it's a voice with an American accent, a very distinctive American accent, and it's this man. because I was lucky enough as a young scientist to attend a lecture course by Feynman, Nobel Prize winning physicist in quantum mechanics. And he was the most astonishing man. And talking to young scientists, one of the things he says, the first principle is you must not fool yourself, because yourself is the easiest person to fool. And that is so wise, so true, so wise. And another one, reality must take precedence over public relations, for nature cannot be fooled. Public relations, he said that in the 60s. We call it spin now. Okay? You can't spin a scientific fact. A scientific fact is a scientific fact. End of. Okay, so is there a consensus behind climate change? Yes, there is. And I thought, how can I demonstrate that? There's a number of studies that reviewed the literature and things. But actually, I thought the IPCC, people have the wrong idea about the IPCC. Yes, it's run by the UN. The number of people who are employed and paid to work on the IPCC, I can count on 2 hands, all right? There's about 10 of them at most. It's all done voluntarily by the climate scientists themselves, very large numbers, all done according to the principles of peer review laid down by Sir Francis Bacon. Except actually a bit more open than that. You can nominate yourself to be a referee, okay? Put in a bad review and they won't use it. Break the rules of peer review, particularly confidentiality, and you get blackballed, okay? But you would from any journal, all right? Another misconception, it's a review journal. That's all it is, and they organise conferences. It's also inclusive. You'll find Henrik's work in there. You'll find my work in there, okay, about solar control of European winters. It's alongside other papers that go, I'm not sure Lockwood's got that right, but that's fine. There isn't a consensus on that yet. Okay, so the IPCC is the climate community trying to tell you there is a consensus view about climate change. Okay, so yes, there is. Right, I don't have time to go through this properly, but the point I'm wanting to make here is how old this science is. By 1900s, Svante Arrhenius had worked out accurately what doubling carbon dioxide in the atmosphere would do. Okay? It's not in terms of all the feedbacks, but the radiative effect. And it all actually comes down to this equation, which actually is not new by any means. It's Joseph Stephan put it together from John Tyndall's observations 15 years earlier. Boltzmann came along with a thermodynamic explanation. And then critically, Planck in the work that actually, in fact, it's interesting. What Planck was trying to do was make light bulbs that emitted more light and less heat. So but it was the founding of quantum mechanics and ended up with us all having mobile phones. Okay. I'm not going to go into it. We can work out how much power per unit area we receive from the sun. We call it the total solar radiance. And it doesn't vary much. In the observations, we find it only varies by about 0.1%. And there's a very, very good scientific reason for that, and that is that the surface of the sun that emits is in good thermal contact with the whole of the convection zone, where you've got large-scale motions bringing heat up to the surface. And that has a huge thermal time constant. Okay? So you can't change the surface temperature quickly, so you can't change the emission quickly. To put it in context, if we turned off the power, the energy flux reaching the bottom of the convection zone now, in 100 years' time, we still wouldn't have noticed any difference in the total solar radiance, all right? So it is very, very hard to change the amount of power we get from the sun simply because of the large mass of the convection zone. And that's why it doesn't vary much. Okay, I don't have time to go into this. We can actually look at what would happen if Earth received that power and just re-radiated it according to the Stefan-Boltzmann law. And you can work out the effective temperature of Earth would be minus 21. Calculation first done by Fourier 200 years ago. And he said something must be warming the Earth beyond that. Okay, absolutely right. 200 years ago. Okay, it was predicted. Incidentally, nobody lives at those temperatures. That's the coldest place on Earth. Average temperature minus 16, and there are 5,000 hardy souls that manage to live there all year round. Okay, so is there a greenhouse effect? Yes, and it's a darn good job there is. Okay. Does carbon dioxide contribute to it? I've given the answer away. Okay, this is 24 hours looking back at Earth by a satellite on its way to Mars. And it measured the spectrum of infrared being emitted by the Earth. It's this black line, and the red line is a model fit. Okay? And the key thing you notice straight away are these bite-outs, where there's less, not no, but less power being emitted. And we can identify what's causing them because the molecules in the atmosphere have vibrations at certain wavelengths, certain frequencies, and they absorb. So you can there's a fingerprint of a given atmospheric constituent, and you can see this is one of the carbon dioxide lines. So yes, it is blocking heat from coming out. Has carbon dioxide risen? I'm not going to spend any time on this. There's no observations that show to argue that it hasn't. And this is actually the level that we find if we analyse bubbles of air that have been trapped in ice sheets. And we're well on the way to being halfway to Svante Arrhenius' doubling of carbon dioxide. We're just about there. So yes, it's risen. Is that rise man-made? There's a number of ways I could show this. I'm just going to show you one, which is the second Seuss effect. And that relies on the fact that carbon dioxide in the atmosphere is exchanged, it's stored in the oceans, but then they give it back, and it's stored in trees, and they die, and they give it back. But some of the biomass gets subducted and gives us our fossil fuels. Now, there's a strange thing that I don't understand, but people who study this stuff do, and that is that biomass, for some reason, likes carbon dioxide that's made with carbon-12 just 2% more than it likes it made from carbon-13. And that isotopic ratio is found in all fossil fuels. So when you burn them, you put back a bit extra carbon dioxide with carbon-12 compared to carbon-13. So what we do is we look at the dilution of carbon-13 over time, and that fall-off is exactly consistent with what we would expect if the rise in carbon dioxide was man-made. It's come from either burning biomass directly or from burning fossil fuels. Okay? There's no doubt. So the answer is yes, it's man-made. Now, what does adding more carbon dioxide increase the greenhouse effect? And there's two arguments used here. What's interesting is they're mutually exclusive. The first argument is that actually it doesn't absorb infrared. But actually, since Tyndall's measurements, we've known that's just not true. Okay? So we can ignore that. The second one is actually, it does absorb, but it's so good that adding some more doesn't make any difference. The absorption lines are said to be saturated. Okay? That actually, I'm afraid, demonstrates a total lack of understanding of how the greenhouse effect works. Let me demonstrate. Here's a carbon dioxide molecule. It's a normal, linear, triatomic molecule. Okay, let's forget about these double covalent bonds. They're not important. We'll have a grey area, which is the molecule. Okay? We give it what we call a short wave. This is solar photon. Okay, one solar photon. It's short wave because the temperature of the surface of the sun is so high. It's high frequency. And carbon dioxide cannot respond at all. Okay? But if we give it a longer wave photon, lower frequency, the sort that Earth transmits because of its lower temperatures, it can set the carbon dioxide oscillating. We call this the symmetric stretch. Or we might give it another one that's a slightly different frequency, and it sets this oscillation going, which we call the asymmetric stretch. Or there's a third one, and it sets off what we call the bending mode. I should say this is greatly exaggerated, okay, just so you can see it. It's a small, high-frequency bending oscillation. Okay, so what happens in the atmosphere? Here it is, an excited molecule that's absorbed a long-wave photon, but it's sitting in a gas that's got a temperature. So what's going on is this, all right? And every so often, one of these interactions allows that de-excitation to happen. It gives off a photon of the same wavelength, and it can do it in any direction. Okay? So let's take a look at our atmosphere. Here are lots of carbon dioxide molecules in the atmosphere. The short wave comes from the sun. This is the spectrum because of the high temperature of the sun. And it goes into the UV. Most of that gets straight down to the ground where it warms it up. But not as much as the surface of the sun, thank goodness. And we get a spectrum here being re-emitted like that, okay, at longer wavelengths. And that's where carbon dioxide can go into these oscillations. So there are windows where some heat can escape through into space. But what happens where it can't? And the answer is that it's going to meet a carbon dioxide. It's got no chance of escaping. There's too much carbon dioxide, okay? And according to idea B, that it's saturated, that's the end of it. But unfortunately, it isn't the end of it. Because eventually that will de-excite and send out a photon which gets absorbed somewhere else. And that could de-excite, it could come down. But overall, there will be some of these photons that get all the way to the top of the atmosphere. And we call this guy being at the top of the atmosphere. It's not really the top of the atmosphere. What it is a height that is high enough that above it there's so little carbon dioxide that this thing's got a chance of de-exciting and emitting into space. That's what it does. Okay? So what happens when we add more carbon dioxide? Okay? Essentially, these photons have to go further before there's little enough carbon dioxide to escape into space. So more CO2 raises this height, which actually makes it colder. So it emits less. Okay? And here's the spectrum of what it emits. Okay? If it's emitting less, we're trapping in more. Okay? So a warmer atmosphere results. There is no way you can saturate a carbon dioxide line. The only way you could saturate it is the temperature of this went to 0, because then it wouldn't emit at all. Okay? So the idea that adding carbon dioxide could not be increasing our temperature is ludicrous. It just defies the theory that was laid down 130 years ago that actually it will do this. Okay? And nobody objected, by the way. What happened for 60 years that nobody bothered to object? And then suddenly it had some unfortunate implications. Oh, and we've got to find something wrong with it. Okay? That's not how science works. Okay, so does increasing carbon dioxide increase the greenhouse effect? The answer is yes. Okay, I don't have time to go into this, but you can ask the question, is the extra carbon dioxide enough to explain the temperature rise? In some ways, the answer is no. Okay? It's about half what you need to explain the temperature rise. And so what we think and what the models say is happening is you have feedback effects that amplify that and give you the other half. Okay? And by the way, I have to call out Ada Lovelace here, Byron's daughter, because she was the first person to actually envisage numerical modelling. And extraordinary, extraordinary feat. Absolutely incredible. When Turing found out that he was following in her footsteps, he was staggered that she'd actually been able to work it out. What we know about models is this: there is a saying, garbage in, garbage out. If something's wrong with the model, your answer will be wrong. Okay? So you've got to be careful. It's always true, that. So what you have to do is actually look at all the models and all the runs of all the models and take them all seriously. You mustn't cherry pick the ones you like. Okay? You must actually look at the whole thing. Okay, let me answer a few more questions. I could go on about that, but I'm not going to. Okay, is irradiance, solar radiance, the cause? I've already said I don't think it can change much, but actually we know it's not the cause. These are maps of temperature change over a 20-year period, and what you've got here is latitude and pressure, and therefore height in the vertical scale. What you're seeing in red is the warming of the troposphere. This is satellite data. And in blue, you're seeing the cooling of the stratosphere. Okay? That is a unique signature of a greenhouse effect. What you're doing is you're trapping in heat, and so the upper layers are cooling because they're getting less heat. Okay? If it were an irradiance factor, this would have warmed as well as the troposphere. Okay? So we know categorically that it's not caused by irradiance changes. I think you'd agree with that, wouldn't you, Hendrik? Yes, good man. I picked a moment where I knew you'd agree. Okay, right. So no. Okay. Why don't I think that other solar magnetic influences could be a factor? Okay, here is a good indicator of solar magnetic activity, the sunspot number. And notice the last cycle that we're just coming to an end of now, cycle 24, was pretty puny. And it's rather similar to one we saw between 1900 and 1910, cycle 14. And then this is my contribution to the whole thing. This is the magnetic flux leaving the sun. These are measurements here in blue, and the purple is a reconstruction based on geomagnetic activity data. And again, you can see cycle 14 and cycle 24 are pretty similar. This is the cosmic ray flux. The dots are directly measured by neutron monitors. The purple is a reconstruction based on cosmogenic isotopes in ice sheets and tree trunks. And again, you see cycle 24 is quite like cycle 14. And yet the temperatures in cycle 14 were way lower than we've had over the last year. And in fact, I heard on the radio on the way up that they think that this decade is going to be the hottest decade we've ever known. Okay, since records began, as they say. So, for me, that's why I don't think solar activity is a factor on a global phase. But I don't want to throw the baby out with the bathwater. There are things like this. Okay, these are, I'm not going to, this is El Nino effects globally. This is a correlation between the temperature at that point and the input. And El Nino obviously warms up the Pacific. This is aerosols from volcanic eruptions. This is man-made effects. And this is the influence of solar activity. And for some reason, Eurasia is particularly prone to, has particularly strong. And I've looked at this, and I think it's a winter effect. It's European winters seem to show a solar influence effect. So I'm not ruling out solar activity effects at all. I believe that they're there. I look for them. But I just don't think they operate on a global scale. How long have I got?
2 minutes.
OK, quick. I just wanted to say a little bit about temperature reconstructions, because these are put together from an enormous, it's not just tree rings or ice sheets, there's an enormous amount of material goes in here. And these have all been put together, and I'll just show you the result. This black line here is the most likely value, the mode of the distribution, and the colours give you the uncertainty, the spread of the distribution. You can see as you go back in time, it gets worse, okay? And then the blue dots are the measured temperature record. And people talk about this dip in the middle being the little ice age, okay? I hate that term because people make up scientific arguments that are pseudo-scientific. They're semantic arguments based on the words little ice age. Okay, it only lasted 250 years and it was only about half a degree deep. Both of those are nothing like a full ice age, okay? And in this country, we have a temperature record that is actually the longest in the world. It's called the Central England temperature. It goes back to 1660. It's measured in a triangle in rural areas, so there's no urban heat islands to worry about, between London, in the main, between London, Lancaster and Bristol. Okay? And here's that reconstructed temperatures, and here's the temperature record. And then you look at the temperature in central England, and you just see how variable it is from year to year. It's really hard to see a trend, although these are the winter months and these are the summer months. And actually, if you look closely, you're just starting to see a warming effect in that warmer winters and warmer summers are becoming more common. Okay? But I want to just look at this year here. Now, this was 1763, I think, or 64. It's the coldest winter in the record. It was cold all over Europe. There was a frost fair. Incidentally, frost fairs have got nothing to do with climate change. They're all to do with the flow of the River Thames. And anyway, we won't go into that. And that's the coldest in the whole record. Look at this. The next winter was the third warmest in the whole record. The idea that it's a little ice age, it was constantly cold during the Maunder minimum, it's nonsense. It just isn't supported by the data. And when you look at the summer, you actually notice that the cold summers are actually caused by volcanic eruptions, okay? That's what does our summers in, okay? So for me, there's interesting things. Oh, by the way, oh no, I've lost the plot. Too late, I'll carry on. Okay, I just wanted to...
2 minutes.
Yeah, 2 minutes again. Okay, it really will be 2 minutes. I just wanted to say something about modern measurement techniques, because this is a wonderful mission. This thing that looks like 2 chicken huts with solar panels on the top. It's called GRACE, Gravity and Climate Explorer. They're about 200 kilometers apart, and they measure that separation incredibly accurately. And the reason it works is that if you fly over something massive like a mountain, the near one gets accelerated first, and then you reach this situation where the mountain's pulling that one back and that one forward, and then you return to normal. And as a way of measuring the mass of a mountain, it's rubbish, but it's very, very good comparing orbit to orbit, seeing the changes. Look at this. This is the weight of the soil in the Amazon, because in winter, it's wetter, okay? And then it dries out in the summer. So you can actually tell how wet the soil in the Amazon is from the gravitational pull, okay? What's that got to do with climate? Well, to start with, it tells you for an absolute certainty we're losing the ice sheets, okay? Not just in area, not even in volume, but in mass. Mass of water is disappearing. Okay, there isn't any scientific doubt about it. Are sea levels rising? Okay, well, this early stuff is tight gauge data, and that's really difficult to use. But this isn't one black line, it's actually about 20. They're arrayed from altimeters on satellites, and they all agree, and you can see sea levels are rising. And from GRACE, we can even tell that actually about 2/3 of that rise is caused by melting ice from the ice sheets, and about 1/3 is because the oceans are warming. And notice how well the altimeter data and the GRACE data marry up. So this is the sort of precision and information that's going into modern climate change. It's not just a bunch of thermometers around the world. Okay, I need to stop. I'm not going to let that go through all that. I should just say thank you for listening and hand over to Henrik.
Well, first of all, thank you very much for inviting me. It's very nice to come back to Birmingham. I was here in 1996 and was actually in Birmingham that this idea about how the sun affects clouds was presented the first time. So Birmingham was the place that really changed my life in more than one way. So I'm going to talk about, my task is somewhat more simple because I'm trying to argue that the sun is important in climate. And the reason I have to do that is because if you look at this IPCC report, then the idea is from this that since 1880 until present, that the forcing from the sun is only 0.05 watt per square meter. It is so small that if this is true, the sun has really no effect on climate. You can completely neglect it. And this value, 0.05, you can compare it to 1.7 watt, which is from CO2, so it's one part of the greenhouse gases. And further, it is also suggested in the latest report that more or less all of the temperature increase is anthropogenic, which is maybe a very strong statement to claim that. So I'm going to talk about a natural impact on climate, which is related to the sun. We have to start by looking at, in the interstellar space, supernovas that goes off. And that means that we have acceleration of particles. It's mainly protons. So this fill up the interstellar space. So you can say that the interstellar space is radioactive because of all of these particles. But these particles seem to be very important for what is going on in our solar system. And that's what I want to talk about. So you have to imagine that we have our solar system and we have the solar wind. And when the sun is active, we have a slightly stronger shield against cosmic rays that are entering into the heliosphere. So when the sun is active, you get fewer of these cosmic rays, and in times where the sun is not very active, you get more of these cosmic rays. And it is important because we can use it in several ways. So they enter into our Earth's atmosphere. And what happens there is that they produce typically what you can see here, a shower structure. And this shower structure has several features. First of all, it produces a lot of ions, so positive and negative charges that are present. Most of the ions that are in the Earth's atmosphere is caused by cosmic rays. But another thing, because the energy is so high, we produce new isotopes, which we call cosmogenic isotopes, like carbon-14. And carbon-14 might go into the biological material here, a tree. And if we then look at a tree ring, then by measuring how much carbon-14 there is in a certain tree ring as a relative to carbon-12, then you can say something about how active the sun was back in time. And you can do that at almost 30,000 years, and certainly 10,000 years, you get a fairly good signal of how solar activity had varied back in time. So The interesting thing is that each time there is a large change in the amount of cosmic rays entering into the atmosphere, there seems to be a change in the Earth's climate. So I want to show you some examples, and it's something that has come up over the last 20 years, and there's actually quite a number of examples. But this is one very beautiful where you see the top figure is carbon-14, so it's a proxy for solar activity. You can see that it is changing, but the bottom, that is oxygen-18, and it has to do likely with the temperature of the Indian Ocean in this case, because it's a cave in Oman where you look at stalagmites, and by measuring the amount of oxygen-18, you get an idea of how climate varied over that period of time. So what you should notice is that there is a beautiful correlation between the two curves. So climate and the changes in solar activity seems to be nicely correlated. Another example is the following. This is a work by Bond, and what you see is present, and this is 12,000 years back in time. And the black curve here is actually it's a proxy for the number of icebergs that have moved over the North Atlantic. So what is happening, because they have been moving down the part of Greenland, they have small grains, and the grains, they fall down on the bottom, and then you can make a sort of a drill, a core, and you can look at these small grains as a function of time. And that says, I mean, the number of grains then says something about how many icebergs were moving over the North Atlantic at that time. But you see the beautiful correlation with the blue curve, which is the changes in carbon-14, a proxy for cosmic rays and solar activity. So these climate changes, I mean, here you have the Little Ice Age. You see that we actually have had many oscillations which are of similar size. And I should say that if we look at this figure here, this is from the ice cores. This is the carbon, this is the CO2 concentration as you get from the ice cores. And what you should notice is that there's no real variations in this. So you cannot explain these climate variations with CO2 here. Here, when we get to the modern period, we see this change. So here we can have an impact. So if we look at the last 1,000 years, you see here a reconstruction of temperatures where you have a Little Ice Age. You have here the changes in cosmic rays or the solar activity. So we have a low solar activity when we have a relatively cold climate. And here we have this is called the medieval warm period. We had the Vikings going to Greenland in this period, and they stayed until about 1420, 1450, and then they disappeared from Greenland. Likely, or at least one idea is it had to do with changes in climate over that period of time. So the question is whether there is a large change in temperature or whether it's very small. And I like the work done by Pollack here, where they try to reconstruct the temperatures back in time from what we call boreholes. So you should imagine that you have a borehole and then you measure the temperature all the way down through the borehole. And from this temperature profile, you can actually say something about how the temperatures changed back in time by you have to invert this signal and then get a temporal change. And of course, as you get further and further back or further down, you have more and more diffusion. So the signal gets worse and worse as you go further and further back in time. But the good thing about this measurement is that you have boreholes for at least 600 places on all continents. So this represents what I would say a global signal, and you get a signal here on the order of 1 degree between 1 and 2 degrees over this period of time. So it looks as if on these long time scales that the sun has had an important effect on climate.
Can you say what the x-axis is?
This is present, and this is 1,000 years back in time, and this is 2,000 years back in time. Sorry. So this was back in time. I want to show you now that also in the modern period we have an impact of solar activity. And it can be done by looking at the energy that goes in and out of the oceans over the 11-year cycle. So what you see here is it's from 1920 until 2000. So here you have the change in sea level rate over this period, and you see this 11-year period which is following more or less very nicely the solar activity. So what is happening is that you have energy from the sun somehow going into the ocean, so it expands. So because of this expansion, you can see it as a sea level change over as a function of time, and you see this very beautiful correlation. So you can say that you're using the oceans as a calorimeter, so you can quantify how much energy is going in and out. Now, it's not just sea level change from it can also be measured by satellites. This is from 1995 to 2000, and here you see a very nice correlation where the only thing that you're using is solar and ENSO fit, and you see a very beautiful correlation between the two curves. Now, when we add this up and put it all together, we find that here we have the satellite. We get that the energy that is going in and out of the oceans over a solar cycle is on between 1 watt and 1.5 watt per square meter. So this is the satellite, this is the tide gauges, that is the sea level. But we can also use sea surface temperature and ocean heat content. They are all, you can say it's 4 independent ways of looking at it. And we get between 1 watt and 1.5 watt. And the interesting thing is that if you look at solar irradiance, it's all the way down here. So we see this is solar irradiance over the 11-year cycle, which we have measured by satellites. So something is amplifying the solar activity. And one of the things, and this is what has been mainly my work, has to do with changes in clouds over this period. So let me summarize what I've said up until this point, that it looks as if we have a significant impact from solar activity on climate. And it looks as if that these temperature variations are in the order of between 1 and 2 degrees over the last 1 or 10,000 years. Now, over these long time scales, we cannot explain it with CO2, so it's sort of out of the picture. And the final thing is that something seems to be capable of amplifying solar activity so that we get on the order of 1 to 1.5 watt over this 11-year cycle. So even though the mechanism I'm talking about is not particularly relevant for the argument that the sun is important, what we believe is going on, I mean, we now have a fairly good idea, and the idea is that we are changing, or the sun is capable of changing the Earth's cloud cover. Now, the sun cools the Earth with about, clouds are cooling the Earth with about 30 watts per square meter. It might be somewhat smaller, but anyhow, if you can make a systematic change in the clouds, you are able to change the energy budget of the Earth. So how are clouds, I mean, how are cosmic rays, how can they change clouds? In order to understand that, or at least to give you an idea, we have to look at how clouds are formed. And in order to form a cloud, you have to have a cloud condensation nuclei in the Earth's atmosphere. It's typically about 50 nanometers. And the reason is that in order to get a cloud droplet, you have to have a surface at which water vapor can condense. And these are cloud condensation nuclei. So the question, of course, is where do these cloud condensation nuclei, and it turns out a large fraction over the oceans are actually produced from a gas phase. So we have ionization by cosmic rays. It produces ions. The ions stick to some of these gas molecules, and it actually stabilizes small clusters. And the idea is that if we have more ionization, we will be able to stabilize more of these small clusters. And then in the end, we will be able to produce even more of these cloud condensation nuclei. And if we change the number of cloud condensation nuclei, we are changing the properties of clouds. And you can see it in this satellite picture here. What you see is a part of I think it's the Pacific, and you have a region here with low clouds, but you notice these stripes here, and these are ship tracks. And you have to imagine that the ship is pumping out, because of the dirty fuel, a lot of small aerosols, which works as cloud condensation nuclei. And you can see by changing the cloud condensation nuclei, you are really changing the optical properties of the clouds. And if you can do this systematically all over the world, you would be able to change the energy budget of the Earth. It would be a very effective way. So this was this original idea that maybe cosmic rays are changing clouds. And I'm now showing you the figure that sort of got me started, got my work started. What you see here is from 83 until 2006. The red curve is change in cosmic rays, and the blue curve is change in low clouds measured by this satellite data set. There's all kinds of problems with satellite data. The calibration, there are problems, and most definitely the latest data are corrupted because of calibration problems. Anyhow, we could test the idea whether cosmic rays are important, or the ionization by cosmic rays is important for production of aerosols. That is the basic physical mechanism that we were interested in. And so the idea is that if we have more ionization, will we then produce more of these small stable aerosols? And we tested that experimentally, and this is the experiments that we did between 2004 and 2007. And what you have on this axis in the increase in cosmic rays, or in the increase in ionization in the chamber. And here we have the small particles that are produced, the small aerosols. And you see that we produce more and more of these small aerosols. So the thing is, there is a mechanism by which we produce small aerosols. I should say that then we spent an enormous amount of time trying to figure out whether these small aerosols could grow to cloud condensation nuclei, because they have to grow almost a factor of 1 million in order to become cloud condensation nuclei. And there has been some controversy about that, but we actually believe we have solved this problem. So not just do ions from cosmic rays help the formation of small aerosols, it also helps the growth into cloud condensation nuclei. Now, people were saying to us that, okay, you have these experiments, but in the real atmosphere, things are so complicated that this mechanism, it might be drowned because there are so many aerosols. So what we have done is trying to, we can actually study the things directly in the atmosphere outside our laboratory. So instead of experiments, we can do observations. And what you see here is sort of the solar atmosphere that you have here. So you don't see the direct light from the sun. It's sort of screened by this there's a shield here. But you have these coronal mass ejection. And if you imagine you have the sun here and you have this plasma coming out, then if it hits the Earth in the right way, then you can have a big drop in the cosmic ray flux. And you can say that that's almost like a natural experiment with the whole Earth. So these events is something that has happened over the last 20 years or more. I mean, it's been happening, but we have data over this period of time, and we can then look what is happening to the aerosols, what is happening to the clouds during these events. And when we do that, we actually see the whole chain from here. This is the drop in cosmic rays because of the solar eruption or the coronal mass ejection. It's called the Phobos decrease when it hits the Earth. And this is 15 days before, and this is where you have the minimum, and then 20 days after. But here you see aerosols measured by Aeronet, and you see you have a drop in the number of aerosols. But you also see that in clouds, this is one satellite system. It is measuring the liquid water of clouds over the oceans. And then we have the MODIS data, another satellite data set, and you see there is a drop in all of them. And the change in the cosmic rays are almost similar in these events to what you have over a solar cycle. And the change in the clouds corresponds to a forcing that is similar to what we would expect, about 1 to 1.5 watt per square meter. So it seems to be fairly consistent with what we expect. So if we now look at this graph that you always see, where you see the greenhouse gases here that have a large effect, I think it's 1.6 or 1.7 watt per square meter from CO2. But if you go down here and you see the changes that you attribute to changes in solar irradiance, they are very small. If we now start to take these changes that I have been seeing in the data into account, then we actually get that the effect since the mountain minimum would be on the order of 1.5 watt per square meter. So it opens the question, how can you reconcile a large effect from the sun with the changes in the greenhouse gases? Because we heard that these, I mean, when you run the models, they fit fairly well with the expectations, and they only use a very small amount of solar activity. The thing is, in order to reconcile it, you have to assume or suggest that the climate sensitivity has to be smaller, the climate sensitivity to CO2. So there are some evidence that climate sensitivity is probably somewhat smaller than what you get from models. And I will show you two examples. What you see here is the response of models to volcanoes. So here, this red line is actually the observations, and the gray band is the result of models. And here you have Krakatoa, and you see that the eruption makes a very large drop in temperature. And each of these here, you see a very large drop in temperature. And if you add up the observations, you see in this published graph here that the change is only about 0.1 degree, whereas the change in the models is about 0.3 to 0.5. So it suggests that the models are exaggerating or too sensitive to climate changes. So the other thing that has been discussed endlessly is that if you have the effect of the greenhouse effect of the anthropogenic, or that is that you get a sort of a heating here in the mid-troposphere. So it should actually heat almost twice as fast in about 5 kilometers in the tropics. And you can actually see that this is really not seen in the observation. So the red and the blue here is the changes in satellite data. And you can see that the models, which are this average here, they seems to be running too hot. So it indicates that maybe the models are exaggerating the effect of CO2. Now, if we look at the different reports that have came out over the last since I think 79 or 78, we have the Charney report. So here you have the climate sensitivity. It says how much the temperature should increase if you double CO2. So it goes between 1.5 degree to about 4.5 degree. And you can see it's interesting, each IPCC report, it is more or less the same, about 3 degrees. But the uncertainty has not really changed, so it's a parameter that's difficult to confine. I think it's important to say that if you take CO2 alone without feedbacks, then you would expect about 1.3 degrees with a doubling of CO2. The rest is actually because you imagine that there's something that is amplifying, we call it the positive feedback. So something is amplifying the effect of increasing the CO2. So you can say it's sort of an instability of the climate system that sort of amplifies the effect. So nearly all of this is because you imagine that it's less cloudy, and maybe there's the more water vapor in the atmosphere. Now, over the years, there's been a lot of studies now. That show that the climate sensitivity seems to be low. Here you have the IPCC range between 1.5 and 4.5 degrees. So what you see here, each of these is a study where they put the climate sensitivity that they got. And what you can see is that the number of studies seems to be going down. So you get a climate sensitivity with very little feedback. That would, of course, suggest the climate would be relatively stable. 2 minutes? 3 minutes. Great. That's exactly what I need. So I want to show you, to give you some quantitative estimates based on a simple climate model where you take into anthropogenic and aerosols and indirect aerosol effects. And you have a mixed layer and you have a deep ocean. And it is where you have parameters, so it's an energy balance type of model. But you can get a very nice agreement with the observation, and the residuals, that is the difference between the observations and the model results, are quite small. And when you do that, you actually get a climate sensitivity which is also small. So this is also, on the order of no feedbacks here. But the thing is that half the warming over the 20th century might actually be partly by solar activity. And if we now make predictions for the future, so this is done by running different scenarios. I think it's a moderate scenario with CO2, but it says that even in these simulations you also have solar effect, and there's even a possibility of a Maunder minimum or a Maunder type minimum in the future. So what you see here is that you don't see a Maunder minimum making a large excursion or something like that, but it's interesting to put it in context with respect to how models are seeing these things. So here you see that the temperature increase based with a lower climate sensitivity gives you at most on the order of 1 degree more than what we have now. And it's much smaller than you get from these climate simulations with large models. So, conclusion. I think we have actual evidence that points to a strong solar climate link and possibly a low climate sensitivity. And I think that would be able to sort of make things fit together. I mean, we actually know the physics behind the link, but it's in some sense irrelevant for this discussion because I believe that solar activity should be taken seriously, but I mean, presently it's actually more or less ignored. Thank you.